questions tonight, and I probably shan't be able to explain all the questions that have come. Is the amount of redshift different in different directions or the same? That is, does it look like we're in the middle of the explosion, or do we know where there is a point where the Big Bang actually sort of happened? Well, it looks as though we're in the middle, but people don't think there is a middle. If you imagine a balloon with coins fixed on the balloon, and then you blow the balloon up, all the coins will get further away from each other as the balloon blows up. The coins won't get bigger, and as someone has just said to me, do galaxies expand? No, the galaxies aren't expanding. The galaxies are staying the same size, but they're getting further apart from each other. Just as the coins on the balloon stay the same size, but as you blow the balloon up, they get further apart from each other. Imagine it's a perfectly spherical balloon, and you sit on one coin, then the next coin to you is moving away a bit slowly, and the next coin away is moving away twice as fast, and the coin further away is moving away faster, so you think you're in the middle and all the coins are moving away from you. But you see, there isn't actually a middle, it's a sphere, and everything is uniformly distributed, and that's why each one thinks they're in the middle. Does that make any sense? So, we don't think that there was sort of a Big Bang over there, woof, and we happen to have been hit over here. We were at the Big Bang. The Big Bang happened here and there. If that makes any sense. We don't know. Let me tell you a prejudice of mine. I like to think that the universe is finite, that it's like a very, very big sphere. Now, I'm probably wrong, but I just find it very hard to imagine an infinite universe. If the Earth is quite a big sphere, and if you go in a long way in one direction, it seems flat, but after a bit you realise it's not flat. And if you go in a really long way, you'll come back over there, having gone right around the Earth. Okay? Now, if the universe is the way I think it might be, you go up towards the nearest star and through to the nearest galaxy and on a straight line and keep on going for a very long time and then come up from there. I may be wrong. But certainly the Big Bang didn't happen in one place over there. It happened, in a sense, everywhere. And there isn't a middle. Come back to me, I mean, that answers one or two. Did the universe explode in just one direction, or did it go in every direction? It went in every direction. Okay? And the redshift is the same in all directions, roughly. What did the Big Bang explode into? Well, the point is, it's impossible to imagine properly, but what the theory says is it's not an empty universe in the middle of which suddenly things appeared and exploded. Rather, before the Big Bang there wasn't any space either, or any time. And since the Big Bang there's been space and time and matter all exploding together. I mean, you can write the equations. I can't imagine it any more than you can. There was another question here which was rather similar about the age of light. How can we tell the age of light coming from a long way away? Well, let me rephrase it. It's actually a very difficult thing to measure how big the universe is. Starting from here, you can measure how far away Scullty is by taking 2 points a long way away and see how the angle differs. Okay, and if you say take sort of 10 yards here and have a telescope there and a telescope there, measure the angle between the telescopes, you can say, Scullty is a mile away. Okay? Okay, if you get on one side of the Earth and the other and see how far the Sun is away, you can see how far the Sun is away. If you take the fact that the Earth goes right round the Sun, then stars appear a slightly different distance away in one time of the year than the other. Do you follow me? It's called parallax. So as the Earth goes round the Sun, the nearest stars shift a little bit. In fact, a parsec is 1 second of arc of parallax. In other words, a star that is 1 parsec away is a star where from one side of the Earth's orbit to the other, the star appears to move by 1 second of arc, which is a 60th of a minute of arc, which is a 60th of a degree. Okay? And a megaparsec is 1,000,000 times further away than that. It is quite difficult to extend this sort of ladder right the way out. It's been a sort of 100 years where we've been trying to extend the distances out, but we now think we have a reasonable idea of the scale of the universe. And therefore, if a galaxy appears to be 1,000 million light years away, then we think that the light has been travelling for 1,000 million light years. It's not that we pick up a phone and say, oh, that's a very old photon. It looks pretty tired to me. I think it's come a long way. So far as we know, and someone's asking about this, so far as we know, photons don't get tired. They might do, but as far as we know, they don't. And therefore, we're not saying this is pretty old light. We're saying it appears to have come from something a very long way away, and that's why it's old. It's been travelling for a long time. Is that clear? Something else about the Big Bang. It's talking about 10 to the minus 9, 1 nanosecond after the Big Bang. If time changes with speed, whose second are we talking about? One of the problems of relativity is that when things are moving very fast, their clock apparently goes slower. We're observing things that appear a very long way away. Are they therefore going to actually go slower because they're moving away from us? Yes, the answer is yes. The red shift is another way of thinking about this. The red shift means things going at a lower frequency. So an atom that gives one particular frequency here and now, if it's going away from us at half the speed of light, it will apparently go a bit slower. It is related to that. So, one of the complications of all this stuff is that you do need to do the calculations using the general theory of relativity, which takes these effects into account. Do you follow me? It is quite difficult, and I'm not an expert, I'm just saying what I've been told. But having said all that, if you imagine here and now is where we'll measure time, and actually this is where the Big Bang was anyway, okay, as well as being everywhere else, then time is the same from that point of view. So I don't think I've answered that properly, but it is possible to, if you do it carefully, to be sure you're dealing with the right time, not time which is 1,000 times too fast or 1,000 times too slow. I believe. I'm conscious I'm shuffling stuff here. Let me come back to this question, which I've only answered part of. Since we can see the stars and the galaxies from every point on Earth, how can you claim that the universe is flat? Yes, when I did a run-through of this to Meg, my wife, she said the same point, and I obviously realised I got it completely, I misunderstood completely what I meant. No, the universe isn't flat in the sense that we look out in all directions and it seems to be the same in every direction. I talked about a balloon with coins on it, and the coins are equally spaced throughout the balloon. Now, change the metaphor. Think of a huge loaf with currents in it. Now the loaf expands, the currents don't expand, but they all move away from each other. Okay, that's the way the universe is. And it's not flat, it's uniform in all directions, like a huge sort of sphere or something. What is flat, and it's maybe not the right word, is the geometry. In other words, if you make very, very big triangles, then the angles still add up to 180 degrees, or 2 right angles, as they do in ordinary Euclidean geometry. It's not like on the Earth, if you make very big triangles, the angles start getting more than 180. Okay? So it's not that the universe is flat, it is that the geometry of the space, or technically the space-time of the universe, is flat, or jolly nearly flat. I don't know whether that's, you know, I'm conscious that it's a term which is, anyway, the universe ain't flat. The universe is uniform everywhere in all directions. The geometry of the universe is technically what is called Euclidean geometry, or flat geometry. And it could have been something else.
So how do you know it's flat geometry? It's not bent somewhere, or you can't measure it a long way away.
Okay, clearly we can't take a piece of string and go out to 10,000 million light years and whatnot. And the technicality, I confess, I don't understand. But I showed you, whether I can get the Ian, and I find that it's that one I want. Whoops. Can I double click on that?
Yeah, should work.
That one there I want. That one. Okay. Here we have the cosmic microwave background radiation. People have done very careful statistics on these patterns. And apparently, if the geometry of the universe wasn't pretty flat, the statistics would be different. Does that make sense? I mean, I'm out of my depth here, but I understand that this is the kind of thing they're doing. They're looking at these variations and looking at the statistics of them and say, well, actually, here we're looking over vast distances of the universe, and if the universe was geometrically sort of spherical, curved, you know, then the patterns will be different. So I think there is some experimental evidence, although we cannot take pieces of string and measure angles. Can the speed of light be explained, or is it just an arbitrary number? We think that the speed of light is a constant. We think it may be related to other things. I mean, light is an electromagnetic wave, so it depends on the way electromagnetic fields interact and so on. So in a sense, there's an explanation of the speed of light. There's actually a practical difficulty, which is it now turns out that the most precise way of defining 1 meter is to say it's the distance that light travels in a certain time. Because of the way in which measurements are now done, we have actually defined the speed of light to be a constant, which is a bit worrying. But what you could detect would be, there are things called dimensionless constants. When you change the units, if you change from feet to meters, you'll get a different number for the speed of light. If you change from seconds to months, you'll get a different number for the speed of light. But there are certain combinations of the numbers that don't change when you change the units, okay? And those are the things, so people do very careful measurements on, you know, things from the far side of the universe. Could they have changed a bit? Well, they could have changed a bit. So far as we know, they haven't. You know, the best evidence so far is that the speed of light is a universal constant. But these are the kind of things that people actually try and do experiments on and say, well, could it have changed? Okay?